Right. Okay, let's get started. One announcement before the class. I updated this announcement section. Please read, this documentation, this data sheet on a private timer. It is very short chapter. So if you open this and password ESEA, right, same. Then chapter 4, right? Here you have private timer. So read. Essentially the same content, right? I explained to you. Very simple. IO device, right? Private timer. So load register, count register, control register, these stuff, right? So only a few pages, right? So it won't take time. So anyway, yeah, please read datasheet. Okay, any question before the class? All right. Okay, so we are talking about some, right? Interworking. We want to mix ARM instructions and some instructions together in your program, right? To refresh your memory, right? So why do you want to use some? For example, you have some program called sorting.c, right? Then you can compile this code using ARM instructions, right? ARM instructions, each instruction is 4 byte in size, right? In ARM case. So you can generate binary, okay? Or you can use some instructions to generate binary, right? Some instruction, you have 2 byte instructions and 4 byte instructions. And then our hope is that using this some instructions, this binary is smaller than this binary. For example, it is like 10 kilobyte. Let's say 10 kilobyte, and this one is 8 kilobyte, for example. So this one is 20% smaller than the binary. Okay, this binary. That is our hope. At the same time, it is providing similar performance to that guy. Performance are similar, right? These two guys are similar performance. Performance means what? Execution time. Right? Similar execution time, but the binary is smaller. So what is the benefit of having a small binary? Small binary means you can use small memory. Small memory means you can create cheaper computer system. Cheaper, right? Because you need a small memory, right? That is the point, right? And in this lecture, we want to mix ARM instructions, some instructions together, right? That is called interworking. Okay. So sometimes you want to call some code from ARM state, right? So call, right? You want to call some code, some to code from ARM state, right? And sometimes you want to call ARM code from some state, right? So when you make a function call, okay, when you make a call, you are supposed to use what instruction? That P L X, branch with the link, branch with the link, and ISA exchange. Okay, PLX label, right? Label or PLX some register, okay, RM. So you can use either of these two to make a function call. Then when you return back, let me do this. When you return, you have to use what? Which instruction? you have to use bx lr instruction when you return, right? The last instruction. Same thing goes to the opposite case, right? You are calling code from some state. Let me just use some, okay? I don't want to use some too, okay? So you are calling, you are making a function call, right? And you use, either of these two, BLX label or BLX RM to make a function call. And when you return, you use the same BXLR instruction. Okay. So that is a recap. Okay, that is a recap. Then then some important information. Let's read this table because it is providing very important information, especially this one. Okay, and this one. Okay, so Chanu, you cannot read? No, 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 cannot. Okay, okay. Chaeyeon, can you please? Can you please read this one, this one, this one?
PLX label branch with link and exchange instruction used to call a subroutine. Always change instruction set between and Thumb2. PLX RM branch and exchange instruction used to call a subroutine branch to a target location in RM. Instruction set Thumb2 is specified in RM0. If RM0 is 0, CPU goes to or remains in state. If RM0 is 1, CPU goes to or remains in Thumb2 state. BXRM, branch and exchange instruction, branch to a target location in RM. Instruction set is specified in RM0. If RM0 is 0, CPU goes to or remains in a Thumb state. And if RM is 1, CPU goes to or remains in Thumb2 state.
Okay. Okay, thanks. First, BLX instruction, right? According to the specification, if you use BLX instruction, it is always changing instruction set. Always changing. So let me show you example code. Better to show you, right? This one and this one together. Okay. So these two, right? So these two are C, function, right? Some code. Okay. So let me show you this one. Some, right? So we have a directive. So you are asking compiler to use some instructions to compile these two functions. Okay. So some. Okay. Some C test. Okay. So this one from some arm state, arm state, you are calling some function. Okay, so use BLX, then it's okay, right? Because you are doing ISA switching, right? ISA switching, but here you are not doing ISA switching, right? You are in arm state, but you are calling arm function, right? Arm C test, which is this C test. So you have directive asking compiler to use ARM instructions to compile this code, right? So here something is strange, but if you look at compiled binary, so let me search. Okay, hold on. Okay, let me search with this label. Search. Okay, this one. So here, right, this BLX instruction, compiler just to use the same, right, BLX instruction in this case. Because compiler knows, right, you are doing ISA switching. But here, compiler figure that you are not doing ISA switching. So that BLX instruction got replaced with BL instruction. Because you are not doing this ISA switching, right? You are from ARM state, you are calling ARM function, right? You are calling ARM function from ARM state, right? So PL. So that is the first one. So anyway, so BLX instruction is always changing ISA, right? So ISA. So you have to look at this compiled binary, code. Look at this one. Then the question is, you have two options, right? Either use BLX label or BLX RM, okay, to make a function call. So the question is, when would you use the first one, and when would you use the second one? BLX label and BLX RM. Okay. So the thing is, if you know the function to call at compile time, right? Not runtime. If you know the function to call at compile time, you are supposed to use the first one, BLX label. So that function call is determined by you, right? At compile time. Compiler knows you are calling this function. But by looking at this, BLX RM, the location you are jumping to is specified in RM. The function you are calling, the function, right? The location, first location of the function, first instruction's location within that function, right? So that is specified in RM, general purpose register, right? So that means at compile time, you don't know which function to call. That is determined at runtime. When you execute it, when you execute the binary, then the function is determined. Okay, so good example is this. Okay, let me show you this example. So this is the one. Let's take a look at this C code. Right? The function pointer example that is defined in main. So scroll it down. Take a look at this one. Okay. So here, make it big. So here, you are taking one argument, right? Which operation you want to do? You are taking this one as an argument. If operation is, look at this, operation is addition plus, then you want to call sum2. Okay, sum2. What is sum2? Sum2 is compiled using some instructions, sum2, right? This function. Okay, and then if this operation, okay, operation is minus, then you want to do subtraction, which is ARM function. Okay, and otherwise, okay, it is not plus or minus. By default, you want to do AND operation, which is compiled using ARM instructions. So that is determined at runtime, right? You don't know which operation you want to do, right? So here, if you go to assembly code, then here we are passing 45, which is minus in ASCII code. Let me show you this. ASCII table. So 45, right? 45 in decimal, right? So that is minus. 43 in decimal, that is plus. So we are passing minus, right? Minus to R0. And according to the calling convention, right? The C code is C code supposed to take argument through R0 register. You have one argument. That is here, right? So argument, right? So you have, in this case, you have two arguments, right? That is passed through R0 and R1 registers. But in this case, you have one argument, right? So R0 register is used to pass argument. So that is why I set this R0 to 45. Okay. Then that is function pointer definition, right? We want to use this FP as a function pointer variable. Function pointer, right? It's very simple concept, right? It is pointing function, right? The location of the function, right? So here, depending on operation, depending on argument you are passing, the function pointer will be set to either this one or that one or AND operation. Then here, look at this, right? So these functions, right? Subtraction, taking two argument, AND operation, two argument, sum, two argument, right? So you are passing 10 and 13. And whatever the operation you are doing, depending on argument, it is doing that operation. So let me execute first. Let me execute this code. Okay. Compile it just in case. Turn on the boot. Okay. And debug. Okay, and let me set breakpoint. Where's that? Okay, here. Right. Set breakpoint, then execute the code until this point, right? Press F8. Okay, there is another breakpoint. Okay, let me remove. Okay, F8. Okay, here, stopped. Okay, now R0 will be set to 45. Okay, 2D in hex, 45 in decimal. Then it is make a function call, right? BLX instruction. Here, you have to be careful, right? We are in ARM state, right? ARM state. So it is not doing ISA switching. Okay, it is not doing ISA switching, right? So main, right? Main, we are in ARM state. Then scroll it down. Still, you are in ARM state. Okay? So if you check out this binary, compile binary, Control C, Control B. Okay. So BLX, that instruction got translated to just branch and link, right? No ISA switching, right? Okay, and here, let me press F5, then it is make a function call, right? F5, then here. Okay, so you are passing what? You are passing minus, so it is supposed to execute, supposed to assign sub2, the location of sub2 function. Okay, let me press F5 here. Okay, then switch, right? So it exit switch statement. So F5 here. Then what do you expect then? If I press F5, then what do you expect? FP, FP function pointer contains the location of this, subtraction. solve. So it is supposed to, this function is supposed to execute this one. Okay, let me press F5. Okay, then what? Then 10 minus 13, so minus 3. Okay, so you are returning minus 3. Then minus 3 will be stored in R0 register. What is minus 3? In computer, you are using 2's complement number system, right? So minus 3 is what? Starting from plus 3, right? 7 in hex, 7 zeros and 3. So flip all the bits, right? So F, then what? 3 is what? 0, 0, 1, 1. So flip all the bits, 1, 1, 0, 0. So that is what? C. And add 1. So D. So 7F's D will be stored in R0 register. I think. Let me press F5. Okay, so you are returned. You haven't returned yet. You are not. You return. You didn't return yet, right? So that will be stored in R0. So FFFD that is stored. Okay, that registered. So you are returning now. Returning, right? Returning. So the result, right? Result. Same value. So 7F and D that will be passed through R0 register to assembly code. Like this. Right? Does it make sense? And going back to this one. So if you check out, compiled binary, we know, the operation, high level operation, right? So now you pass minus. So this switch statement will select this statement. Okay. Then this function execute the subtraction, then return, right? So let's take a look at assembly, how a compiler translated this code. Okay. This one, C. Okay, take a look at this. Take a look at this. Okay. So here, first, this statement. Okay. So it is trying to, the compiler is trying to cook up the location of this function, sum2, which happens to be, I think, look at this. So by looking at this, what is that? I don't know. So probably if you interpret this code and this code, then I think the function sum2 starts from what? So we haven't studied that instruction, right? Move W, move T. But by looking at this, I can roughly figure out what it is doing. So I think it is doing. It is trying to create a number. What number? 16 is 10, right? So 10, then upper 16-bit, and this one lower 16-bit. 0, 6, 3, 5. It is trying to create this number, I think. The sum2 location. Let me search with sum2. C, F, B, sum2. Okay, this one, this location. The symbol, right? Sum2 function or symbol or label that is located at this location. That is placed at this location. 6, 3, 4. Okay, 6, 3, why then 5? It is very strange, right? Why odd number? It's supposed to be, even number, right? Because each instruction, some instruction is either 2 byte or 4 byte. ARM instruction 4 byte, right? That means the LSB, the least significant bit, supposed to be 0, right? LSB. But in this case, what is 5? In binary, 0, 1, 0, 1. So 1. So odd number, right? Very strange. Why? Because of this, right? Because of this. RM LSB is 1. CPU goes to some state. Okay. So let me search sum2. If you look at this high level code, sum2, right? Sum2 is what? Sum2 is compiled using some instructions. Okay, some instructions. Okay. This one compiled using some instructions. Sub2, that is what? Web directive. Right. So ARM, it is using ARM instructions, and this one also using ARM instructions. Okay. So trying to cook up, trying to create that, odd number, trying to set, right? Compiler is setting LSB. So the function location, actual location is 4, right? Actual location is 4. So 1, 0, 1, 0, 0. But, compiler figured out that, okay, that function, sum2, sum2 is, sum2 function. Okay, I have to use different name. Sum2 is sum2, right? This function is compiled. So it is using sum2 instructions, right? So the compiler is setting this bit to 1. So 5. Okay. So let's go to, and how about this? Okay, scroll it down. And how about sub2? By looking at this, similar instruction, similar sequence, right? Move and move, right? Move and move. So 1, 0, 6, 8, 8 in this case, right? This one is sum2 and sub2. Okay. 0x1, 0, then what? 6, 8, 8. 0, 6, 8, 8. The start location of that sub2. Okay. So if you are curious, then search with sub2. Start location, right? 1, 0, 0, 6, 8, 8. Right? Okay. How about end 2? End 2. 1, 6B8. 6B8. Search. 6B8. Look at this. 6B8. Right? 1, 0, 6B8. Okay. And the one thing you have to be careful. One thing you have to be note is, look at this one. Store instruction. Right? So R3 register contains the location of this, the start location of that function. R3 register contains start location of that function. R3 register contains start location of that function. And that is stored to same location. FP frame pointer -8, frame pointer -8, frame pointer -8. Frame pointer is R11, R11 register. And when you make a function call, you are storing, right? And here you are reading from that same position. You are making a function call here, right? You stored start location of the function at this location, right? Store instruction, store instruction, store instruction. So depending on your choice, depending on switch statement, right? Depending on argument, right? Depending on argument you are passing, you are selecting which function you want to execute. And that start location is stored at that location in memory. Okay. And when you make a function call, then you are reading from that location. Okay. FP plus 8, FP minus 8, FP minus 8, right? FP minus 8, we are reading, right? Reading. Then BRX here. Branch and link with ISA change, right? So, so I'm trying to explain this instruction. Okay, when would you use that instruction? Okay. That instruction can be used when the function you want to call is dynamically determined. You don't know at compile time, right? Does it make sense? Any question about this? And if you look at this example, I'm trying to look at this. Okay. So here main, right? Main, you are in ARM state. Then scroll it down. BLX instruction to make a function call with ISA change. Then I did some experiment. What if I use this one? So it is not, it is not good example, right? So I'm trying to use BLX RM instruction to make a function call, but I know, right? I know which function I want to call, right? This is a function I want to call, but just for test, right? I'm storing this label, function name, symbol to R0 register and using BLX. Okay, then what do you think? Then some assembly test by looking at this name, you are calling some code, right? Some code. Then then LSB, right? LSB of R0 register supposed to be 1, right? Here. LSB is 1, then CPU goes to CPU is switching, right? What if I add UR between line 52? Okay, let me show you this code. Then probably I can add, right? I can add. I don't know. Good question. Probably I can test. Okay, so let me show you a first example. Okay, so the thing is, you want to do ISA switching. So here you are in ARM state. Then you are calling some function, some, right? So that means R0 LSB is supposed to be 1. The question is, really? Compiler is setting R0 register to 1. LSB of R0 register to 1. That is the question. Let me save it and compile it. Compile the code. Again, this is not good example, right? So this instruction, when the function you want to call is dynamically determined, you use that instruction. But in this case, it is not dynamically determined. You already know, right? You are calling this function, right? So, but just for test. So Juan, you are trying to hack the ARM CPU, right? You want to test this here, some weird code. That is actually good. That is that is very good. Yes. Okay. then download it. Okay, then set breakpoint to here probably. Okay, press F8. Oops, what happened? Running. Okay, something went wrong. Okay, let me close it and do it again. I don't know. Some okay. Okay, then I set breakpoint right here. Too many breakpoint probably. I don't know. 52. So let me remove breakpoint. 52. Okay, 52. 52. Okay, press F8. Okay, stop here. Registers. Then R0 register, right? So what is that instruction for? You are storing the location of this function to R0 register. Okay, and then let me search the binary FB. So that is located at 5E8. Okay. 5E8 10 0. Okay, 5E8. Then it is really setting R0 register to 5E8. Let me execute it. F5. Check out this. 5E9. 5E9. Okay, so let's go through here. So the compiler knows, right? This function starts from 5E8, but it is some instructions. So you are doing instructions that change, right? So let me search with 5E9. It's supposed somewhere, right? So here. So compiler stored this number, this address to this memory location. Okay, this one, 5E9. Okay, and then reading from that memory location, 10618, I think. If you execute that code, where is that? Where is that? Okay, this one, I think. This one, right? This one, you are reading from. So you are reading PC plus 68 from this location, add 68. I think that is that location, this location, to read this value. Okay. So, the point is, you are setting R0 register with this, symbol location, right? But the compiler is setting LSB because the compiler knows you are calling, you are doing, you are calling, this, some function, right? Then F5, then ISA switch, right? So CPSR, then T bit is 1, right? ISA switch. Okay, then let me answer. I don't know. Let me add what Juhan suggested. I don't know what would happen. Okay, so let me anyway add which code? EOR R0 R0. You want to clear that bit, right? Is it correct code? I don't know. You have to put sharp 1, right? That's okay. Juan, what do you think? What would happen? I don't know. You are trying to set LSB to 0, right? You are forcing, right? LSB to 0. then execute this one. Then what do you expect? No ISA switching, even though you are calling some function, right? Then what do you think? The first instruction is what? Okay, so some SEM test. Okay, SEM test. SEM test. Okay, so if you look at this, you know, this is the first instruction. Push is the first instruction. Okay, in this function. Then that happens to be B500. Yes, I think, yeah, Juan, I think exception would happen. So what do you mean? Exception is the topic after midterm exam. So my guesstimation, my guess is if you do this operation, okay. So if you do this operation, you are setting LSB to 0, then execute BLX instruction. Okay. Then CPU is not doing, CPU is, it is strange, right? It is strange, BLX. Okay, let me check. Sorry. BLX, still BLX, right? Still BLX. So it is trying to, so it is, you know, doing ISA switching. Because BLX instruction, right? BLX, always change instruction set. But LSB is not, LSB, oh, okay, sorry. This is one, okay? BLX, this one. Okay, sorry, this one. R0, right? You are forcing LSB to LSB. Okay, R0 register to 0, right? Then R0. Compiler use still BLX, meaning ISA switching, but LSB of R0 register here. LSB of R0 register is 0, meaning you stay in ARM state, right? Are you guys with me? So I think here you are in ARM state, right? Before you making a function call, okay? Trying to call some function, right? This one, some function. But the problem is LSB of R0 register is 0. So that means CPU will stay in ARM state. In ARM state, you are trying to execute some instruction. We have some problem, right? I think so. That means CPU does not understand, right? CPU is in ARM state and fetch some instruction. The CPU does not know what to do, right? So I'm expecting ARM instruction, but you are feeding me some instruction. Right? So CPU cannot interpret that machine code. So that is exceptional event. So CPU does not know what to do, right? So some exception will happen, I think. Let me execute it, okay? Show you. I think that is the case. Set breakpoint. Still, right? Breakpoint. Line 52. Okay, F8. So registers. So R0 is 5ED. Okay, odd number D, right? 1101 D in binary. So execute this, then D will be C, right? 5 is C. Okay, Then what? F5, then what? Okay, let me, exception, I think. Okay, okay. No exception. Sum, right? You are in ARM state, right? J0, 0. Let me press F5. Okay, exception. So that is undefined. Okay, so we will talk about that. Okay, after midterm exam. So that means CPU cannot interpret that machine code. That means undefined instruction exception. Undefined instruction. CPU read the instruction from memory, and CPU cannot. CPU does not know what to do. Okay, CPU cannot interpret that machine code because it is expecting ARM instruction, not some instruction. Okay. Okay, Juan, you had fun? Okay. Any question? Any other question? So this one is called the interrupt vector table. Okay, so we will talk about that, after midterm exam when we discuss interrupt and exception. Okay, that is super important topic. Okay, that is the one. So you're not supposed to do this. Okay, unless you are doing something bad to your smartphone. Smartphone is based on ARM, right? Okay, that is the one. Okay, so that is the one. Okay, we talked, I think, enough about this BLX instruction to make a function call and instruction set switch and BXRM to return back to the caller. Okay. Okay, that is, I think, everything. Okay, let's continue to talk about PowerPoint. Okay, then calling convention. The slide from slide 8 to 13. I think that is, I already explained with the demo example. You can just go through. So here, so ARM code. You are in ARM state, right? You are calling ARM function, some function here, ARM function, right? So in this case, you are not doing any, ISA switching. So next slide. So compiled version, right? Even though you write the BLX instruction, compiler replaced that instruction with BL. Okay, that is the one. Okay, next one here. BLX RM example, some example, but this is not good, example, right? Because typical usage of this instruction is when the function you call is dynamically determined, but in this case it is statically determined, but just for test, right? There is the one. So here, function pointer example, right? BLX instruction, then compiled version, right? So compiler is trying to cook up the location, sum2, okay, sub2, and end2. Then you are making a function call. Okay, so that is the one. And what is this? Okay, you are calling ARM function from some state. Right? You are in some state and calling ARM function. Okay, so there is one. Okay, you can check out this slide. Can move on. Then next topic. Okay, this one is Hojun. Can you please?
Make the next 1 to 4 instruction conditional. Any conditional code may be used. Doesn't affect condition flags. 16-bit instructions in block do not affect condition flags except CMP, CMN, and TST. 32-bit instructions in block do affect condition flags. Normal rules apply. Current if-then status stored in CPSR. Conditional block may be safely interrupted and return to. Not recommended to branch into or out of if then block.
Okay, thanks. If you recall ARM, the first lecture on ARM instructions. So let me open this. So here, most ARM instructions can be conditionally executed, right? So if you look at this machine code format of ARM instruction, first 4-bit are condition field, right? Condition field. So you can in basic base instruction, you can add these one of these suffix EQ, any, and so on, right? That is encoded. That is encoded in the machine code, right? 4-bit. Okay. So the most ARM instructions can be conditionally executed. But in case of some, first slide. So in case of some, right? In case of some, think about some instructions. Some is providing 2-byte instruction and 4-byte instruction, right? So within 2-byte, 16-bit encoding space, some, right? Some instruction. You have to specify operation code, OP code. You have to specify RM, RD, and so on. So you don't have field for condition code, right? You don't want to reserve 4-bit as a condition, field, condition code, right? Simply you don't have enough bit this encoding space. So that is why some instruction is providing, some two instruction is not basically providing conditional execution, and it is providing limited support for conditional execution, very limited support for conditional execution. Okay, so it looks very funny if you look at this example, right? So let me show you the first example. Okay, so let's say you want to write this high level code in some assembly. So depending on this condition, you execute +2 or +4. Okay, how would you implement? How would you write assembly, sum2 assembly like this? Okay, look at this. Okay, compare R0 and 0. Compare these two. Then compare instruction will update flags. Okay, flags. Then this one looks very funny. IT, if then instruction. Sum is providing if then instruction. That is a syntax. Okay, so it means if then else. Okay, T is then, E is else, then else. So inside this IT block, you can have here, you can have up to 4 instructions. Up to 4 instructions. 1 instruction, 2 instruction, 3 or 4 instructions. Okay, no more than that. Okay, up to 4 instructions in this case. So you are specifying this condition. Okay, EQ. Okay, so by looking at this, okay, these 2 instructions will be executed if 0 flag is set. Okay, and next 2 instruction will be executed if 0 flag is not set. Okay, so look at this. This one you are reading. Okay, this dereference in C. That dereference, right? Dereference operator. You are reading from memory, right? So LDR memory read, right? EQ reading from R1 location, then add 2. Okay, and not equal condition. You are reading from R2. Okay, then add 4, right? And then so some more example. So what if you want to implement this high level code? Then first compare, right? R0 and 0. Then now you have two, you have two, one under then block. Okay. If condition is met, then block, right? Then let's call this then block. Okay. Else. Then let's call this else block. So in that example, you have one instruction in then block, right? And here one instruction in else block. So here you have to say if then, if one then else, one else. In the previous example, right? In the previous example, if then two instructions, then else, two instructions in else block. Okay, here you have one instruction in then block. Okay, one instruction in else block. So you have to use if then else. Then condition is what? Condition is EQ. Condition you have to check is EQ. Okay, how about this? Okay, this is the same one. So let me. Okay, how about this? So now, so in this case, okay, we are doing this. It looks very weird, right? And stupid, right? If one instruction in then block, else, right? Three instructions in else block. The condition is GT. Probably you are doing this. You are doing greater than. Okay. And here, if then. In this case, if then HS, higher or same, I think, right? Higher or same, unsigned number. GT, I think signed number. Okay, this one unsigned number. So in this case, then one instruction in then block, and no instruction, nothing in else, one then. Okay, so let me play with this code. Okay, so I have some example. Some example here. So let me copy everything. Okay, copy everything. C to here. So this is conditional statement in sum, right? You can have up to 4 instructions after this one. Okay, the condition is EQ. Okay, so what if you do this? What if you EQ? So 2 EQ, 2 instructions in then block. Okay, 2 instructions. So you have to specify EQ and EQ. Okay, and else. So 2 instructions in else block. Okay. So what if you do this? What if, okay? So even though I specified then else, then what if I do this any? So it is not consistent, right? 2 instructions in then, here, right? 2 instructions in then and 2 instructions in else. You specify that with IT. But here, 1 instruction in then, 3 instructions in else. So if you do this, compiler will complain. Compiler will refuse to compile the code. Okay. Close this. Okay, here we have some problem, right? So incorrect condition in IT block. Okay, so incorrect condition, you have to use, you must use EQ here. Otherwise, compiler will refuse to compile. Okay, and one more thing. So let me execute. Let me first show you a demo, even though it is very intuitive and simple, too simple to show. But anyway, let me show you. So here R0 is 1, R1 is 2. So compare, right? So NGCV, those flags will be updated. So these two are different. R0 and R1 different. So that means these two will not be executed. Okay, these two will be executed. Right? Because 1 and 2. So 1 and 2. These two are not equal. Right? Let me why is so long. Okay. Some 2. Okay, and set breakpoint here. Here 75. Remove. Okay, F8. Stop here. Then R0 is 1, right? R0 is 1, R1 is 2. So you are comparing, right? So NGCV in CPSR flags will be set. The important thing is 0 flag, right? 0 flag will be 0, right? Because these two are not equal. 1 and 2 not equal. 0 flag is still 0, right? So here, so let me execute. Let me explain in depth about this instruction. What is the effect of that instruction in hardware? Okay, we will talk in detail, but function first. Okay, function. So then else. So that means it is not doing anything. It is not updating any register. Okay, it is updating actually CPSR register. Okay, let me show you here. So here in CPSR register, you have IT field, 8-bit IT field. Okay, and that instruction will update this 8-bit, this orange, okay, IT field. Okay, let me execute it. Okay, 5. So something got changed. Your CPSR here, IT 07. Okay, so now okay, these two, R0 is what? R0 is 1 and 2, right? So this one will not be executed, right? So no change in R0 and R1. No change. Then here, plus 4, right? So 5 and 6. 5 and 6. Okay. So that is a function. Okay, function first. And so let me change this code to it sounds very simple, right? But if you think a little bit in depth, then something is very strange, right? So let's take a look at this. Let me compile. Equal, equal, not equal, not equal. Same, right? R0 plus 2, R0 plus 2, R1 plus 2, and R1 plus 2. So machine code is supposed to be different, right? Because EQ suffix, NE suffix. But let me compile it. Show you the machine code. Look at this. Add EQ. Okay. 3002. Add not equal 3002. Same machine code, right? Same machine code. Right? So these two. Add EQ R1 plus 2. 3102. Not equal, right? EQ not equal. Not equal. 3102. 3102. Same machine code. And the question is, how does CPU know which instruction to execute and which instruction should be nullified? The secret is IT. Secret is IT. Even though machine code is the same, when CPU execute these instructions, hardware will check IT and these flags together to make decision, execution or nullify decision. We'll talk in depth about that. But I don't think we have enough time. That is taking, I think, at least 20 minutes. So let me play some, code. What if you do this here? What if you comment out something like this? If you do this, then compiler also refused to compile because you specified two instructions in then block, okay, and two instructions in else block. Okay, so let me compile it. Try to compile it. Okay, instruction not allowed in IT block. It is talking about this subtraction because next instruction after this is subtraction. So you are supposed to have some suffix any here. Okay, so that is complaining. What if you do this? Okay, EQ any. Okay, what if I specify GT? That is also illegal, right? You said base condition is EQ. Then you are supposed to specify EQ inside the then statement and opposite condition, any and any. Else, right? If then else, right? If then else. Then statement, else is opposite condition. So you are not supposed to use GT. You have to use NE. That is illegal, right? So let's compile it. Okay, incorrect, right? So you must use NE like this. Okay, otherwise it refused to compile. Okay, any question about this? Any question about this function? 충분히. 찬우, do you think so? So how come? ITTE로도 충분히 구분 가능할 것 같은 서비스를. I think that is okay. I see what you're saying. I think there is a syntax problem, and I think if you don't specify anything like this, then I don't know, because what do you think? If you don't specify anything and say, okay, these two are inside then block, and next two are inside else block, that is implicit. Probably you can say, okay, even though you specify anything, okay, specify anything, you would say, okay, that is implicit. So these two are inside the then, these two are inside the else. But I think people want to make it more, specific and clear. EQ, then it is very clear. EQ, then any and any, it is clear, right? So these four are inside this, conditional block, right? So the syntax problem, right? Syntax issue, and I think again, people want to make it and clear and explicit, right? Because if you remove this, then sometimes confusing, right? Okay. Any other questions? Okay, then okay, so I think we can finish a little early today, and next time on Thursday we will talk about in depth about the mechanism, how ARM CPU is doing that comparison. What comparison? That EQ. Okay, if you look at the ARM instruction, CPU is doing some comparison, right? A comparison of what? The suffix, EQ, GT suffix, and the condition code. Sorry, these flags. Confusing, right? So let me open. Some internal number 2. So I drew hardware block diagram. So conditional execution in ARM, right? So some instruction, for example, arithmetic or compare instruction is updating NGCV. I have some, okay. So this one, subtraction instruction, for example, that is updating NGCV because you have S suffix, right? And next instruction, EQ, okay? When CPU execute next instruction, that instruction is, it is fed into control unit, right? Control unit. So EQ condition is encoded in 4 MSB, most significant bit, and CPU make the decision, okay, execute this instruction or not by comparing this condition code, EQ, and EQ against these, flags. These flags and OP code, compared to make the decision. Right? Hardware will compare. Okay, and then yes, same thing should happen in some 2 instruction, right? You specified then else, then to execute, to determine, execute, or nullify decision, no operation decision. CPU should do some comparison, right? These flags against, this IT block. We will talk in detail about that. Okay, next time. So if you know some internal, mechanism, hardware mechanism, then things would be super clear. Right? So you don't have to memorize the syntax. Things would be super clear, I think. So that is why, the understanding the underlying hardware is very important. You don't have to memorize, things. Okay, understand, feel, right? That is important. All right, that is for today. Okay, I'll see you next time. Bye. Okay, thanks.